So today's lecture we are going to see syntax, context-free grammars and constituency parsing. Syntax refers to the set of rules, principles and process that govern the structure of the sentence in language. As we have seen in the previous slides, how words are being formed and group of words, how phrases are being formed, and we are also see different kind of NLP algorithms that are required to understand the language in different levels of linguistic thing. So today we are going to talk about how it's been useful for the sentence formation and what kind of analysis we can make to understand the sentence and what are the algorithms and techniques that are available in NLP. So the rules determine how words, phrases are combined to form well-structured sentences. So there are two concepts, one is well-formedness, another one is ill-formedness. A sentence is well-formed if it follows the syntactic rules of a language. So that means a language, every language has some kind of set of rules, right? So for example, we have I am happy. So this is a well-formed sentence structure in English where the sentence starts with the subject and there is a verb and there is an adjective. Right. So on the other hand, if we give a sentence like I saw girl the tall, it is an unacceptable and also ungrammatical. And these kind of sentences we call it as ill-formed sentences. So syntax helps to identify these grammatical errors by enforcing a structure to it. The key concepts in syntax are, we should be knowing that there are different kind of syntactic categories that have some kind of similar behavior. For example, the lexical categories include nouns, as we have already seen in part of speech tagging, verbs, adjectives and adverbs. And the functional categories include determiners, preposition. In the case of Indian languages, most of our languages have postposition, where the case marking always occurs after the word or as a suffix to the word, and also conjunction. So when you have the cat sat on the mat, we know that the pure tagging of everything, but when you see the mat or the cat together forms one kind of phrase, right? So this kind of phrase here, what we call is a noun phrase. So there are different kind of phrasal categories we need to understand when we are looking at the sentence. One is noun phrase. This noun phrase is nothing but a group of words that function as a noun in a sentence. For example, John, it's a very simple NP. That means NP is a noun phrase, right? It can have only N, or the little boy, where the is a determiner and little is an adjective and boy is a noun, right? So it can have NP with a determiner and adjective followed by the node. Actually, the important node here is noun. Similarly, the cat on the mat, here there is an NP and followed by there is a preposition and there is an NP. This preposition and NP together constitute something called prepositional phrase, right? So now the phrase structure rule, what we understood is NP can have optionally a determiner, NP can have optionally any number of adjectives. You can say the little, tall, beautiful girl or a boy, and it definitely need to have noun where you cannot drop it, and it can also have optionally PP. So on the other hand, verb phrases are phrases that includes verb and its complementizers or complements and modifiers. So for example, verb phrase can have simple VP as she runs, where runs is a VP, or it can have a VP with an object, whereas John sang a song, and it can also have a VP which has a V and another NP and followed by one more PP. So, and also it can have multiple adverbs followed by. So if you look at the VP structure rule, it can have a V. In English, it's always V comes in the beginning of the phrase, and any number of NPs, star here is any number, and the parenthesis means it is optional, and there is one PP and any number of adverbs that can follow. But on the other hand, if you look at Indian languages, the verb will not occur in this direction. It occurs in the end of the whole sentence. So English kind of languages are called as left branching languages, whereas Indian languages are branching towards the right side. So prepositional phrase is another kind of phrasal category. It begins with a preposition and followed by a noun phrase. For example, in the house with a friend, where PP can have P, one P at least, followed by NP. So now phrase structure grammar is nothing but it's a type of generative grammar. We try to identify the syntactic structure of the sentence using the phrases that we have seen. It can be a noun phrase, verb phrase, or a prepositional phrase. So it breaks down the sentences into constituent parts, as we have seen, NP, PP and BP. So for example, if you have the cat sat on the mat, the phrase structure grammar tries to give a tree something like this, where it originates with something called sentence. That's a very important note, and sentence is rewritten as NP and VP, and NP has determiner and noun, VP has V, and recursively it can have a PP and PP can have another NP. So you could see the cat sat on the mat is expressed through some kind of structure over here. So this structure will help us in identifying whether a particular sentence generated by the machine is a right formed sentence that goes along with the language grammar or not. So the phrase structure rule here expresses is sentence is rewritten as NP and VP. NP is nothing but it is a determiner and V, the similar thing, and VP is VP, PP, and PP is PNP. So now the sentence structure, as we see, the most structure is every sentence starts with S, and it can have NP and VP. And a sentence is ill-formed if it does not follow the basic structure. So when you say the dog cannot be a complete sentence because there is a missing of VP, and barked cannot be a complete sentence, that is a missing of NP. So now again we also should have an idea on what are clauses in languages, as phrases are minimum information which we are trying to group them locally to understand how it constitutes. On the other hand, types of clauses is something like a clause is a kind of sentence where it can stand alone or it need not be standalone all the time. It depends on the another clause. So when it is standalone, we call it as an independent clause. So something like I went to the store. When it depends on another clause, we call it as a dependent clause. For example, if I go out, it cannot stand on its own. So you need to have another independent clause to finish this sentence. So there are different type of sentences. Some sentences are simple where there is only one independent clause. Some sentences are compound where two or more independent clause can be combined together, and some sentences are complex where we have at least one independent followed by one dependent or more dependent clauses, and compound complex where we have two independent clauses but one or more dependent clauses. So similarly, different kind of clauses can be put together to make our sentences in languages are very simple to complex to more complex kind of nature. Okay, so the complexities in language, especially in the coming to the syntactic pattern, comes through different pattern. One is because of ambiguities. Ambiguities can occur in structural way. For example, I saw a man with a telescope. Now, who has the telescope? Whether man has the telescope or I have a telescope, it is an ambiguous thing. This is structural ambiguity. Coordination ambiguity occurs when there are coordinators where, for example, there is a coordinator like and, now old man and women. Now this old goes to only men, or we have something like old man and woman where old can be actually jointly used with both men and women, right? So this kind of coordination ambiguity occurs in languages. And garden path sentences, as we have already seen in PO's categories, that that initially helps us to identify the structure in a different way, but when we are finally reading that complete sentence, we are getting a different sense. For example, the old man, the boat, as we see, whether the man is a part of NP or is a part of VP. And recursiveness is another ambiguity or another complexity in syntax. Here the structure repeats itself within a sentence. For example, this is the cat that ate the rat that ate the cheese, right? So we can have multiple sentences which are combined together, and it makes a very complex construction in languages. And ellipses, where we are omitting some of the words, though we are omitting it, we can understand it through context. For example, I did it, he didn't. So he didn't do it, that's not required. We are omitting that whole part, but still we can make a meaning out of it. Okay, let's understand something called context-free grammar. So context-free grammar is nothing but a grammar. It's a formal system. It describes the syntax of a natural language. It uses the production rules, so it helps us in understanding how words and phrases are combined together to form a meaningful construction. So again, it consists of non-terminal symbols like NP and VP, and it has some terminal symbols like flight, the kind of words, and it has also production rules where we are telling S is rewritten as NPVP, and it also designated starting symbol, that is S. So the phrase structure grammar that we have already seen, it is a more of formal understanding of language part to make sure that how sentences are being formed. On the other hand, context-free grammars are built for computationally understand how words are grouped together to make a sentence. So for example, if you say sentence is rewritten as NPVP, here sentence consists of noun phrase and a verb phrase. So now CFG rules expresses how these symbols can be rewritten with other symbols. So when you see NP, NP is rewritten as determiner unnominal, that is called N. VP, verb, NP, nominal can be a noun or any other nominal form. Now the symbols on the left of the arrow are non-terminal symbols, and with those right on the terminals are either it can be a terminal or non-terminal, but most of them the other sides are non-terminal symbols. Now NP is rewritten as determiner nominal. It can be a determiner noun, and it is nothing but the and flight. Now the flight is a valid noun phrase. Now how we can build an automatic parser which uses this CFG grammar so that we can build a tree. So now parsing is a concept. Again, it is an automatic process to assign some kind of syntactic structure similar to a kind of tree to a sentence according to the grammar of a particular language. So parse trees are mostly a graphical representation. It helps us in understand how the sentences are being formed. Now each node represents a symbol, and its children represent what it can be rewritten into CFG rules. So for example, when you have something like a flight, now a flight can be derived from this kind of rules like NP. It has a determiner and nominal. Determiner is nothing but a, and nominal form is nothing but here it is a noun. Nominal can be a noun, pronoun, or any other nominal phrases which can be substituted in the place of an NP under the nominal category. A noun is nothing but a flight. So this generates the following parse tree for us. Now we have language 0, and we have also have a lexicon for that language 0, let's say. Now these grammatical rules we have seen so far, now we will call them as L0. And now we can use the symbols like OR symbols as a kind of pipe symbol which indicate a non-terminal, and they have possible extension. So nouns can be rewritten as flights, flight, breeze, trip, morning. Similarly, all other categories can be substituted with some kind of elements that can be substituted with a particular category. So these complete thing what we call it as a lexicon. Now Now this lexicon helps us in understanding, okay, there are grammatical rules in languages. Let's say sentence is rewritten as NP-VP, and NP can be a pronoun, proper noun, or a determiner and a nominal, or nominal can be a nominal noun, or it can be just a noun without any kind of compound form, and VP can also have multiple things. Now this is the grammar, let's say example grammar of L0, where we are trying to like generate the sentence using the handful of grammar rules. Now the parse tree for I prefer a morning flight according to the grammar, that is L0 here is. So, okay, I prefer a morning flight. Now there is an NP and VP, and this VP has another V and NP, and NP has determiner and nominal. So the output looks like this. Now, we can also represent the parse tree in a more compact format, which are called as bracketed notation. And this bracketed notation looks something like in a linear format instead of a tree structure format, where you have a sentence, this is nothing but NP, the whole NP and the whole VP, and within VP you have another NP, okay, and a verb. Right. So this whole thing is expressed in a bracketed format. So most of the time the constituency grammar or constituency parsing looks at the sentence, trying to identify the constituents within the sentence and represent it either in the tree format or as a bracketed format. Now the tree banks are another important concept that we need to understand. It is a corpus which every sentence is annotated with some parse tree. It can be a context-free grammar, or it can be some other grammars like dependency grammar. So the tree bank is a vast corpus in a language where we are trying to identify the different kind of sentence structure and try to give them the roles or identify different kind of grammatical pattern it carries. Now the role of this tree banks are, it's crucial for parsing, also to do some kind of linguistic investigation to understand the syntactic behavior of a language. Now mostly it's done by human, okay, human handcrafted this kind of rules and annotate the data with the kind of guideline that they follow, and they build it initially. Now the most very popular tree banks are pen tree bank, which includes English, Arabic, Chinese tree banks, and also we do have universal dependency tree banks and Paninian dependency tree banks from the Indian side. So all these tree banks are a rich linguistic representation of a language. And here when they follow context-free grammar algorithm, they use either Lisp style where they parenthesize the notation, or they use the standard node and line trees. For example, you could see there is a the parse tree from the pen tree bank. You could see either they are a kind of Lisp format where there is an NP which is a subject, that is that cold empty sky. So JJ is given for adjectives. So there is a VP was full of fire and light, right? So similarly the different notation is given here. Now the tree corresponding to the brown corpus sentence for the same previous sentence is also being expressed in this way. The cold, empty sky, you could see JJ or two JJs with the commas, and there is a VB. These are all pure tagging that we have understood, and each one of them are grouped together and trying to make sure that they are a kind of acceptable formats in that language. Now CFG grammar rules. How does this CFG grammar rules are being made? Now we are building the grammar for each of the pattern in a language. Once this grammar is ready, we have a lexicon where the terminal things need to be addressed with the substitutable lexical item in the language. So this is the lexicon and this is the grammar of a language. Now CFG rules from pen tree bank, how it is being done. Now the sentences in the tree bank implicitly constitute a grammar of the language. So now parsed sentences are extracted. Since the grammar used in the pen Treebank is a very flat, so they lead to many grammars. So approximately around 4,500 different rules for expanding only VP are identified in the pen Treebank. Now similarly, there are a lot of variation in how the PP is formed in languages like English. So for example case, VP can be VBD with PP, VP can be VBD with PPP, or any number of PPs, and different kind of other rules are being formed. Now these CFG grammars are the most important thing for building the parser. Now grammar equivalence is another thing that we need to understand. The two grammars are strongly equivalent. Let's say you have two different kind of tree banks. We are trying to create two grammars out of these two tree banks. If they are strongly equivalent, if they generate same set of rules. If not, that means they are two different varieties of a language or two different languages. Similarly, the grammars are weakly equivalent if they generate the same set of strings, but they do not necessarily assign the same phrase structure. Now, Chomsky normal form is nothing but it is a context-free grammar. Here each rule is in the form of, let's say, A is rewritten as BC with non-terminal, or A with terminal node like A, where it is a lexicon. Now, where A, B, C are non-terminal, whereas A is a terminal. It cannot have an empty production in this CNF format. Now, binary branching is another important thing here. CNF ensures that every rule leads to binary branching, meaning that each rule breaks down into at least two components. So, the conversion is another important thing, because context-free grammar can be converted into CNF. So, when you have rules like A is rewritten as B, C, D, it has to split into two binary rules where A is rewritten as B and X is rewritten as C and D. So, this kind of conversion will help us in coming up with a very regular pattern of languages. So, also to reduce the branching, so that grammar patterns are also being handful now. Now, you could see now this is the miniature of English grammar and a small part of lexicon. So, English grammar is something like a miniature form as we just have seen. So, this grammar with this help of lexicon, we are able to generate the grammatically acceptable sentences. So, now ambiguities are very common problem in languages. So, it occurs when we are able to parse the sentences in more than one way. So, it can be a structural ambiguity or it can be a lexical ambiguity. Now, we know that I saw the man with the telescope can be interpreted in two multiple ways. One is I used the telescope to see the man, or the man I saw had a telescope, right? Okay, now let's take this sentence and create two different kind of trees to show how these trees can help us in disambiguating the sense. Let's say I am starting with an S, and S is nothing but NP and VP, and NP is nothing but N here, this is I, and VP is V, and there is an NP, and also there is a PP. Now this is saw, and let's say this is, in short we are writing it as something like this, and PP is with the telescope. And similarly, let's say we are doing another tree for this sentence where there is an NP and a VP, and again NP is an N which is an I, and VP is a verb, and there is an NP, and this is sa, and let's say this NP branches as N and again another PP, and this PP goes into with the telescope, and this NP into the man. Now see, the PP attachment in different places renders two different senses. Now when it comes to the constituency parsing, we are trying to analyze the sentence with the kind of information that we have used now. So we are trying to create different kind of phrases and trying to put those phrases and try to fit these phrases with the language data that we have. So when you say the cat sat on the mat, now there is an NP which is the cat and there is a VP that is sat on the mat. Now what are the constituents in the natural language? Constituents are nothing but they are words that function as a single unit in a sentence. So it can be like constituents which we can try to test through different kind of tests like substitution. When you substitute the cat with it, and movement and coordination kind of test, linguistic text can help us to make sure something is a constituent or not. Now Harry the horse arrived, and here the Harry the horse can be substituted with he, showing that it forms the constituent. And we have to also understand something called CKY parsing, which actually a very stronger parsing algorithm which comes through the CNF, that is a Chomsky normal form. So it's a dynamic programming based approach to the parsing. So here this handles the language data in a more systematic way so that it explores all possible substructures of a sentence. So it's particularly useful when we want to identify the possible parse trees for a given sentence which also has an ambiguity. For example, it requires the grammar to be in the CNF format, where we know about the CNF format already, where A is, let's say, written as BC, and or A can be with the terminal node, where A, B, C are non-terminal, is a terminal. Now we can convert it into CNF by eliminating some kind of epsilon ellipsis rules or unit production and ensuring that all productions are in the binary branching. So now this is the illustration where L1 grammar and its conversion to its CNF format. So CNF format always gives you a very neat format with the binary featuring from the one node to another node. So now this algorithm, what it does, it takes the parsing table and examine all the possible substrings of the input sentence, and it goes into each of the parts, split the part into two ways and applies the grammar which forms the constituent. Now the table is filled in a bottom-up manner, starting with the smallest substrings and working up into the full sentence. The presence of start symbol spanning the entire input in the parse tree indicates that the sentence is grammatically correct. Now let's take the example, book the flight through Houston. Now the parse table initialization is, it start filling the cells corresponding to single words using the lexical rules that we have identified, and it is iteratively fill the table by combining entries based on binary rules used from CNF. And if NP and VP are found, it checks the rules that can combine them into larger constituents. Now the goal is to fill the top right cell with the start symbol. Now the step-by-step thing tells us we'll start with an initialization with all the part of speech and fill the table as we just explained, and finally understand whether there is an S symbol, that is the sentence. Now the key advantage is it handles the ambiguous sentences and provides all possible trees for the ambiguous thing. So let's show this one in the illustration. Now it starts from the down part, fill the whole words into some kind of pure tagging and try to fill it, try to eliminate the things which cannot be combined together, reaches to the final position and finally identifies whether there is something called S or not. So let's say the same sentence, book the flight through Houston. The initial thing is it identifies all the part of speech over here and the basic constituents. Once it identifies, it starts to look at, okay, there is an NP, is this NP, what is the part that can be attached to? So it can be attached to the PP, and this PP can have another note which is a P, right? So similarly it goes travel from one stage to another. Again PP can have and be under of nominal, and it can have another noun, and this nominal can be a part of an NP and it can have a determiner, And finally, we are reaching out to this kind of understanding where there is a kind of node which all can be attached, where there is a sentence over here. And this sentence can also have a nominal form, and this nominal, so in this particular sentence there is no noun, because book the flight through Houston, here it is whole thing is a VP, and this VP is a part of sentence. Now yes is actually you book the flight, right, which is elided in this sentence. So the whole thing is identified with the VP, which has a verb, and it also have another NP associated with it. So now the and flight are combined together in another NP, and through Houston is combined to another PP, within which it can also is a part of the NP node. Now it's efficient for parsing because it avoids redundant computation by storing the results in as a sub problems. So ambiguity handling is very rich because it can build multiple parse trees by maintaining all possible constitution in the parse table. So the limitation is it will increase the grammar size and the complexity. If we are able to capture all kind of grammatical pattern in that language, it will be easier to do it. Now, it's widely been used in again NLP applications like syntax checking, especially the sentence formation, grammar checking kind of thing, and understand the language part, and also it's a foundation for some of the advanced parsing algorithm. Now, the summary is syntax defines the structure of sentences. It specifies how words are combined to form grammatically correct sentence. The categories like noun, verb, adjectives, it helps to categorize the words based on the grammatical rules. And the phrasal categories like NP, VP, PP, which are nothing but it represents the group of words so that we are try to get the single syntactic unit. And constituency parsing helps us in breaking down the sentences into their constituents so that we are identifying how words are grouped together. And context-free grammar helps us to give the formal system to describe sentence structure using the production rules. And CKY parsing is an efficient algorithm for parsing sentences using the CNF format. So now Treebanks are the most important stuffs because there we are trying to build some kind of linguistically rich information where the sentences are annotated with the kind of information that are being explained here, so that it helps us to extract the rules, and also the relation across the words and their phrases can also be extracted through this particular task.